Welcome back, guys. Guys, got a very quick lesson over here. And this is kind of quick. I'm kind of doing this in a different order than you guys see in your textbook. I think this one makes a bit more sense, and then the next example is going to be the next lesson to be quite a bit longer because of the way I'm doing it here. Something we call higher order derivatives. Okay, so we're going to start for this guy over here. F of x equals x to the fifth, and we want to calculate the derivative. So that means f prime of x equals 5x to the fourth. We are only using our power rule. Okay, very simple question over here. Now what is this next, guys? Like, well, so what does the second derivative mean? The second derivative means the derivative of the derivative. That's what the second derivative means, okay? So if f prime of x equals 5x to the fourth, that means f double prime of x, this is the notation we use for the second derivative here, is going to equal 20x cubed, okay? Now the third derivative is a derivative of this guy over here, equals 60x squared, okay? Now the fourth derivative, you will see notation like this sometimes, guys. Like, first, second, third derivatives are often written like this, and the fourth derivative just might be written like this. You might see 4 ticks, but I mean, it's just, you're not going to have to write all these ticks over and over and over again, guys. So we just going to write f to the fourth of x. It's going to be the derivative of this guy over here, which would be 120x. Okay, so guys, here's the idea for this question over here: the first, second, third. So the derivative, second, third, and fourth derivatives. You're just taking derivatives of derivatives for these guys over here. Okay. What does this mean? Like that, in terms of like, well, we're going to talk about that, guys, in our next unit, which we call applications of derivatives. Okay. So it kind of in terms of a graph, what does a second derivative represent and stuff like that, and we'll talk about that one later on over here. All right. One more example here. You guys, I kind of realized that we haven't been using this notation too much, but this over here, if we have y equals this is what we call Leibniz notation. So Leibniz notation. It's pretty much, guys, they're considered like 2 major founders of calculus. One of them was Isaac Newton. He was one of them, and the other guy was this mathematician named Leibniz. And so when he was talking about derivatives like that, he used this notation as well. Okay, this means the exact same thing. It means y prime or f prime of x. It means the exact same thing over there. Okay, so that's how we do this. What we call that Leibniz notation. Okay, so if I have y equals x to the 1/2, my is going to equal 1 over 2 x to the negative 1/2. Okay, so that'd be my first derivative over here. Okay, or sorry, I should have done this in Leibniz notation like this in dy dx, which means, so this just means the derivative of y with respect to x. The derivative of y with respect to x. Okay. All right. So all this means over here, oops, this should be d3y dx cubed. Okay. This just means the third derivative. Okay. So just different notation you guys might see. Third derivative. Okay. So we know that dy dx equals 1/2 x to the negative 1/2. That means the second derivative, I'll write like this, is going to equal negative 1/4 x to the negative 3 over 2. So the negative 1/2 comes down, becomes a negative 1/4 like this, and we'll go 1 less. And then the third derivative, negative 3 over 2 comes down. So negative 3 over 2 times negative 1/4 is 3 over 8 x to the negative 5 over 2. And guys, you can just leave your answer just like that. All right, guys, very short lesson over here, higher order derivatives. And we're going to be using this idea again in the next topic over here, guys, and it's going to get more complex in a second.